Welcome back to linear algebra. In this video, I wanted to look at change of basis transformations. We know that any vector space can be defined entirely by a set of basis vectors. Every vector space has infinitely many, but for our purposes, at least one set of basis vectors, and every vector in the vector space can be written as a linear combination of those basis vectors. So starting with here are basis vectors, build a vector space around them is a very potent way of talking about vector spaces. Of course, every vector space has not just one set of basis vectors, but infinitely many sets of basis vectors. So very often there's an interesting question to be asked. If we know how to represent a vector in one set of basis vectors, can we use that information to represent the vector in a different set of basis vectors? And so let me get my head out of the way and let's talk through just that. So we start with a vector space V, and we have two bases, B1, B2 down through to Bn, U1, U2 down through to Un. Remember that for any vector space, the number of vectors in a basis for that vector space is constant. It's the dimension of the vector space. So B and S both have n vectors, the same number of vectors. And because they are both bases for these, we know that for any little v in vector space V, we can write V as some A1 times B1 plus A2 times B2 plus all the way down to AN times BN. Or we can write V as some C1 times U1, some C2 times U2, all the way down to Cn times Un. So the question here, if we know A1, A2, down through to AN as an ordered n tuple, right? We know all of the coefficients to represent V using basis vector in set B. And we want to know, can we find the representations of the C's? And again, some vocabulary here. This is the representation of V under B, which you'll sometimes see written square bracket V subscript B. And then this one would be the representation of V under S, square bracket V subscript S. I'm not too worried about the notation there, but I did want to at least mention it because if you're looking up these ideas in our textbook or in other sources, you are probably going to come across that notation. I claim that a change of basis is a linear transformation. And it is defined the representation of vector v under space S is a1 times the representation of b1 under vector space S, a2 times the representation of b2 under S, all the way down to an times the representation of bn under S. I'm not going to go through and try to prove in detail that this transformation will work. I do want to talk through the argument because I think it's an interesting one. But if you stop and think about it for just a few moments, it should make very clear sense to you. Let me scroll up a little bit so we can look at the representation of V under basis B. That's this one right here. Because S is a basis, I know that there is a way to write B1 as a linear combination of the vectors in S. So it's some C1 times U1 plus C2 times U2 all the way down to Cn times UN. I can do that for vector B1. I can do that for vector B2. I can do that all the way down to vector Bn. And that's literally what I'm trying to say here. I'm going to take B1 and I'm going to write it as a linear combination of the vectors in S. I know I can do that because B1 is in the vector space and S is a basis for the vector space. That's what it means to be a basis. The only way that S is a basis is if every vector, including B1, can be written as a linear combination. And so if we have a basis that we are comfortable with, if we have a new basis we are going into, and we can write all of the original basis vectors in terms of the new basis vectors, then we have a linear transformation and we can move onward with it. Finding that transformation is sometimes easier said than done. I think there's enough going on here that it's worth taking the time to talk about this for Euclidean vectors first. So I'm going to take the standard unit basis vectors for the Euclidean vector space R3. So that's 1, 0, 0, 0, 1, 0, and 0, 0, 1. And let's take a new set of basis vectors. I'll call it S, which is going to start off very similarly. Let's make this 3-dimension instead of 4-dimension. I'm going to start off with 1, 0, 0, the same first vector. That's kind of boring, but it gets interesting from there. Then I'm going to take 1, 1, 0, and I'm going to take 1, 1, 1 as my new set of vectors. To show that this is a basis, we need to check linear independence. We know that R3 is a three-dimensional vector space, so we know that it takes three vectors to span the space. If we have three linearly independent vectors, that will be enough to span R3. So if you take the time and check to see that these are linearly independent vectors, you have verified that this is in fact a basis. I'm not going to do that here because I'm more interested in the transformation, but that is something that you absolutely can do. And if you're interested, I encourage you to take some time to do that. But in order to write the transformation, we need to figure out how to take all three of our original basis vectors and write them as linear combinations of the new basis vectors. The first one is pretty easy. 1, 0, 0, if I want to rewrite that under S, is simply 1 times 1, 0, 0. If I really want to be technically correct about this, I can mention that I also have 0 times 1, 1, 0, and 0 times 1, 1, 1. But you can do that first one by inspection. It's the same vector. The second one gets to be a little bit trickier. If I want to take 0, 1, 0 and represent it under S, that means I'm going to need some C1 times 1, 0, 0 plus C2 times 1, 1, 0 plus C3 times 1, 1, 1. If I expand out on the right-hand side, I have the first component is C1 plus C2 plus C3. The second component is C2 plus C3, and the third component is C3. All right, that's a system of equations that I could solve using any of the techniques for solving systems of equations we have talked about. In this particular case, it's really easy to do by inspection. The bottom row tells me immediately that C3 is equal to 0. Plug that result into the second row, immediately tells me that C2 is equal to 1. And plug both of those results into the first row, and I get that C1 plus 1 is equal to 0, which means that C1 itself must be negative 1. So 0, 1, 0 under S is negative 1 times 1, 0, 0 plus 1 times 1, 1, 0 plus 0 times 1, 1, 1. And I'm not going to go through and do the algebra again, but you can show that if you want 0, 0, 1 under S, it's going to be 0 times 1, 0, 0 minus 1 times 1, 1, 0 and positive 1 times 1, 1, 1. Right? The algebra is exactly the same idea as what we did before, just change the left-hand side. And the system of equations works basically the same way. All right, so not all that difficult to come across, but it gives us our transformation. And so, if I have an arbitrary vector, and I'm going to actually do this for an arbitrary vector, A, B, C, that I want to represent under S. Well, representing the arbitrary vector under the original basis vectors is pretty straightforward. It's A times 1, 0, 0. and B times 0, 1, 0, and C times 0, 0, 1. Then, writing the representation for each of these vectors under S. 1, 0, 0 was 1 times 1, 0, 0 plus 0 times 1, 1, 0 plus 0 times 1, 1, 1. 0, 1, 0 was negative 1 times 1, 0, 0, positive 1 times 1, 1, 0, and 0 times 1, 1, 1. 0, 0, 1 was 0 times the first basis vector, negative 1 times the second basis vector, positive 1 times the third basis vector. Multiplying with ordered triples isn't really a thing that we've done. It's not really a thing we can do, but we know that we can think of these as themselves being three-dimensional vectors and use the operations we're accustomed to here. So the ordered pairs, if we do that, would be A minus B, B minus C, and C. And just doing that is a shorthand. It makes it so that you don't have to worry about what the vectors themselves are. But we could just as easily write this as A minus B times the first vector of our new basis, 1, 0, 0, plus B minus C times our second vector, 1, 1, 0, plus C times our last vector, 1, 1, 1. And if you go through and you simplify this, you will be able to get back to the original ABC, but that's not what's interesting. What's interesting here is that we have a linear transformation, although the notation for it is a little bit goofy. And we can do the same sort of thing for vectors of other sorts as well. Right? This doesn't have to be restricted to Euclidean vectors. In P2, I'm sorry, I don't want P2. I want P1, the set of all linear polynomials. We can use as a basis for the set of all linear polynomials the functions 1 and x. I claim that I can write any basis vector as a linear combination, or I can write any linear polynomial as a linear combination of the basis vectors 1 plus x and 1 minus x. If you want to, I encourage you to take the time to verify that S is a basis. I'm not going to be grading on that. I'm not going to be specifically looking for it, but it's always worth doing. The new skill, the thing that I want you to pay attention to is for a generic linear polynomial, a naught plus a1 times x, find the representation of this under the new basis S. All right, take a couple of minutes, see what you can do with that, and I'll see you in the next video.